All right, so let's move on. We are still discussing atomic structure, and in the last class we have discussed the Rutherford atom model and the Bohr atom model, and we saw that the Bohr atom model introduced for the first time the idea that the state of the electron in an atom is quantized, but the Bohr model didn't explain why. The Bohr model also only worked for the hydrogen atom, but not for all the other atoms. And I told you that essentially the reason for this is that the Bohr atom model still doesn't account for a very important quantity or a very important property of the electron, which is the wave-particle dualism. And the last part of the last class, we then discussed the wave-particle dualism for electromagnetic radiation, which was discovered as a result of the investigation of the photoelectric effect by Albert Einstein. So originally, it was believed that this wave-particle dualism is only valid for electromagnetic radiation and the photon respectively. However, today we know that the wave-particle dualism is applicable for all particles, or at least it hasn't been disproved for any particle that could be investigated experimentally in a meaningful way. Okay. So now the first one who introduced the idea that wave-particle dualism is not only applicable to the photon, but to all particles was Louis de Broglie. So he said that the formula developed by Albert Einstein, which says that the wavelength of the electromagnetic radiation is equal to h over m times c, which is the velocity of the light, okay, which would be equal to the velocity of the photon, would be true for all particles. The only modification to that formula that one would need to make is to replace the velocity of light by the velocity of the respective particle. So that means that any particle that would have a certain velocity would have these properties. In particular, one could measure a wavelength associated with it. So this originally was a very radical idea, which was not well received originally. Louis de Broglie was a PhD student, a graduate student, when he originally proposed the idea, and his PhD thesis was almost not accepted because the idea was so speculative. But it turned out to be correct, as proven by electron diffraction experiments later, and led to a Nobel Prize for him as a consequence. So now let us discuss how we can explain that the electron has wave properties, and which wave properties in particular it has within an atom. Okay, so now in order to understand this, we first need to understand what standing waves are, because essentially an electron in an atom behaves similarly to a standing wave. So what is a standing wave in general? Let me illustrate this first by an example. So for instance, a vibrating guitar string is a standing wave, or in other words, the vibrations of the guitar string can be described by standing waves. And these standing waves can only have certain frequencies and certain wavelengths. This is essentially because the standing wave is confined. Okay, so for instance, when you plug a guitar string, then the waves that you actually produce by that, they are confined within the guitar string, which is only a fixed length. Okay, so that confinement of the wave that is actually triggered leads to a standing wave, which is naturally quantized. That means that only certain frequencies, only certain wavelengths are allowed for that standing wave. Okay, so you know that a guitar string can only vibrate at certain frequencies. Okay, that's why the guitar string produces a specific tone. Okay, and you see the allowed frequencies here. So you have the so-called ground vibration. So this is this one. So this has the longest possible wavelength, and the wavelength would be in this case just 2 times the length of the guitar string. Okay, because the wavelength is always defined as the as a 4 period. Okay, so this wave here until here makes only half of a period, and we need basically 2 times the length of the guitar string to make that period complete. So that's the so-called ground vibration, but in addition to that, you can also have what is called higher harmonics. Okay, so you see here the first higher harmonic. Okay, so you see here that the wavelength of the associated vibration is equal to the length of the guitar string. Okay, so here you see that we have a vibration which has a wavelength which is 2/3 of the length of the guitar string. Here it's half of the length of the guitar string, and so forth. Okay, so you see that only discrete wavelengths are allowed. We can say that the standing waves associated with the allowed vibrations are quantized. Okay, so now one can very easily cast these vibrations within a simple formula, and the length of the wavelengths are lambda are equal to 2 times L, so that's in this case the length of the guitar string, over an integer quantum number n. Okay, so for this vibration here, n would be 1. For this vibration here, n would be 2. For this vibration here, n would be 3, and so forth. So I should perhaps mention also why these waves are actually called standing waves. Okay, they are called standing waves because the position of the nodes and the peaks of the waves are fixed on the guitar string. Okay, they occur on a fixed position on the guitar string. All right, so for instance here, for this one, we see that the maxima and the minimum is exactly in the middle of the guitar string. Yeah, okay, it doesn't move along the guitar string. So for this wave here, we have here the first maximum, minimum, which stays at its position. We have here a second one. Yeah? And we see that in the middle here, we have a node. So the node is where the algebraic sign of the wave changes. Okay? The algebraic sign of the amplitude of the wave, to be precise. So you see that the node here is also at a constant position on the guitar string. So this is what characterizes as standing waves. The crests and the troughs and the nodes, they do not move on the guitar string or on the wave in general. Okay, so I should mention that that standing wave is in a way actually an illusion. So it actually is created by the interference of two waves that are actually traveling. And that is actually illustrated over here. So now when you actually pluck the guitar string, okay, you trigger actually waves on that guitar string, and these waves move. Okay, and they move toward the end of the guitar string in opposite direction. But at the end, they're getting reflected. Okay, and they start moving into the opposite direction. Okay, and now they're interfering. Okay, but they continue to travel until they again reach the end of the guitar strings where they get reflected again. Okay, so you actually have an interference pattern between two traveling waves that travel into the opposite direction and are getting reflected at the points where the wave is actually being confined. Okay, and that interference pattern then produces actually the standing wave. You see this actually here. So you see a negative traveling wave here in red, okay, a positive traveling wave here in green, and what is blue is then the standing wave, which is the interference pattern, which is nothing as the addition of the negative traveling wave and the positive traveling wave. Okay, whereby the negative and the positive traveling wave always gets basically reflected at the ends. Okay, now what inspired scientists to think that an electron could behave like a standing wave? That's because standing waves are being quantized, and Bohr is discovered where the states of the electron in an atom are also quantized. So possibly the reason for this quantization is that the electron behaves like a standing wave, which are also quantized, okay, due to the wave properties of the electron. Okay, so now the question was, of course, how could one describe the electron in an atom as a wave, as a standing wave in particular? So before we go to this more complex problem, let's first look at a somewhat more simple problem, which is the electron in a one-dimensional box. We can say also an electron traveling back and forth on a line. Okay? So now let us assume here a one-dimensional box which walls that are infinitely high. Okay? Because the walls are infinitely high, we can say, well, the potential energy of the electron within these walls would be infinitely high, but the electron can never get out of the one-dimensional box just because the walls are infinitely high. Okay, so within the box, the potential energy of our electron is zero. Okay, because it's just always at the bottom of the box. Yeah, but it can have kinetic energy, so it can actually move at the bottom of the box. So our box is in this case a one-dimensional box, and that means that it has only one coordinate. It can call this coordinate x, okay, and the length of the box would then be defined by a. Okay, so x could be vary between 0 and a. So because of our electron can have kinetic energy, it can actually travel inside of the box. But because the box is one-dimensional, it can travel only on a line. Okay. So now let us assume what happens when our electron travels on that line. Well, it can travel so and so far into one direction until it hits the wall. So what will happen once it hits the wall? Well, it can actually it will be reflected and travels into the opposite direction until it hits the wall again. Okay, this time the other wall, and then it's getting reflected again, traveling the opposite direction until, well, it hits again the wall. So this is actually animated here. You see, our electron is constantly traveling back and forth between the walls. Right? So now we need to consider now that our electron is not a classical particle. It has not only these particle properties, but it also has wave properties. And therefore, we can say that, well, as our electron travels, okay, there's also always a wave traveling back and forth, and back and forth. Yeah. And now these waves can again interfere, and as they interfere, they would produce a standing wave, which would then describe the electron as a standing wave due to its particle properties. Okay. Okay, and the fact that our electron is confined within the box. Okay, so basically this motion would result in standing waves. You see them here animated again with different wavelengths due to the wave properties of the electron. So now how can we describe this more quantitatively with the help of mathematics? So can we actually develop wave functions that would describe the electron as a standing wave? Okay. We would expect that this wave function would be quantized. So our wave function would be a function of a quantum number, but what exact mathematical form would it actually have? So now let us develop that in the following. So from classical wave mechanics, this differential equation here is known. So this differential equation we take for granted, and we believe that it is applicable to standing matter waves in general. Okay, so this here is a differential equation which says that basically the second derivative of the wave function that describes the standing wave is equal to minus 2 times pi over lambda square, whereby lambda is the wavelength of the wave times the wave function that describes the wave. All right. So now we have to apply this expression now to the electron in the one-dimensional box, and I see there's something here in the chat. The node is also where there is zero possibility of finding the electron right too. Yeah, that is actually correct, but we will get to that later. Okay, so far we have only discussed about standing waves in general. Now, yeah, the nodes actually represent a place where the probability to find the electron is zero. I will talk about this in a moment. Okay, so now we said previously that our electron, oops. Our electron can have a kinetic energy. So the kinetic energy of a particle is given by the formula a half mv squared. So now we can make some mathematical rearrangements. We can multiply this equation by m and divide also by m. Then the equation becomes mv squared over 2m. Okay, we've just multiplied with m in the numerator and in the denominator at the same time. And then we can just solve this equation for mv squared, and then mv squared is equal to 2 times m times e. Okay. So now we can take the square root of that, and then that means that m times v is equal to the square root of 2 times m times e. So now why have we done this? Because the next step, we have to consider the wave particle dualism of the electron. Okay, so far we have treated the electron only as a classical particle. So according to that, lambda is equal to h over m times v. We can solve this equation for m times v, then m times v is h divided by lambda, okay? And then we can plug this expression here into this equation, okay? And then solve this for lambda, and then lambda is equal to h over m 2me to the power of half. All right, so now we have lambda under the consideration of the wave-particle dualism. So we can now insert this expression here into this differential equation. We substitute lambda here by this expression, okay? And then we have accounted for the wave-particle dualism of the electron, okay? And have basically applied this equation here, this general equation, specifically to the electron. Okay? So, well, as we do this, the right-hand side of this equation becomes just 4 pi square em2 over h square. And then we can do just simple rearrangement. So we can actually move everything in here except the energy to the left side, okay? And then the left side becomes, well, d square over dx square times minus h square over 8 pi square m, okay? So 4 times 2 is 8, so that 8 moves here into the denominator, okay? So pi square moves into the denominator on the other side, and h square moves here into the numerator, and well, that minus sign is also carried over to the other side. Okay, so this expression is equal to the kinetic energy of our electron times the wave function that describes our electron. Okay, so now this is called the Schrödinger equation for the electron in a one-dimensional box. In another view, it says that we have here an operator for the kinetic energy of our electron that, when applied to the wave function, gives you the kinetic energy of the wave function. Okay, so now in the next step, we need to solve this differential equation because what we actually want to know is the wave function that describes the electron in the one-dimensional box. So there are different ways to mathematically solve differential equations. One is to guess a solution and afterwards prove that that solution is correct, and that's the approach that we are taking here. So we propose a very generic wave function as a solution and then refine that very generic wave function. So a very generic wave function has the following form. It has a sinus component and a cosinus component with different coefficients, a and b in front of the sinus and the cosinus term, and r and s in front of x, which represents the coordinate within our one-dimensional box. Okay, so now we need to think about, well, how can we refine this very generic solution so that it fits our problem? So now we need to think about boundary conditions this wave function needs to fulfill. So one boundary condition is, one property it needs to have is that the amplitude of the wave function, psi, must be 0 at x is equal to 0. Okay, so x equal to 0 is basically the first end in our one-dimensional box. Okay, why must our amplitude to be 0? That's because when you look back at the example of the guitar string, basically the amplitude of the wave at the point where the guitar string is being pinned down must be naturally zero. Just because the guitar string is pinned down in an analogous situation we would expect for an electron in the one-dimensional box, where the walls begin, where the amplitude will have to become zero because the potential energy will need to become infinite. Okay, so now that implies that B has to be zero, because only when B is zero, the entire cosinus term becomes zero. Okay, so a sinus term can be zero or is zero at x is equal to zero, but whenever we would add a cosinus term, our amplitude would be zero. Therefore, this coefficient must be zero in order to make that entire term zero. So basically, that simplifies our wave function, and our wave function becomes psi is equal to A times sinus Rx. Okay. So now at the other end of the one-dimensional box, for the same reason, the amplitude must also be zero. Okay. So psi must be zero where x is equal to A. Okay. So now a sinus term is only zero at integer multiples of pi. Okay. Therefore, R times A must be equal to an integer number n or quantum number n times pi. Okay. So we can solve this equation for R, and then R is equal to n times pi over A. So now that defines what R needs to be in order to fulfill the second boundary condition. Okay, only when R is equal to n times pi over A, okay, then psi becomes zero at n times pi, meaning it becomes also zero at the, well, end of the one-dimensional box. Okay, so now that defines our wave function as follows: psi is equal to A times sinus of n times pi times x over A. So we see that our wave function is now a function of a quantum number n, telling us that our wave function is being quantized. Okay, and well, the different wave functions that result for the different quantum number n's would describe now the allowed states that our electron could have in our one-dimensional box. So the final result is that our electron does not behave like a like a classical particle, where basically any state would be allowed, but only certain states are allowed that correspond to, well, different quantum numbers that correlate to different standing waves that electron can adopt in our one-dimensional box. So again, you see here the shape of the wave functions for the different quantum numbers. Here for n equal to 1, okay, we have the wave with the longest wavelength. Okay, we don't have any node here. For n equal to 2, we have one node. For n equal to 3, we have two nodes. For n equal to 4, we have three nodes, and so forth. Okay, so now we are, however, still not quite finished, because we still do not know what our coefficient A is. So how do we find our coefficient A? We find it when we consider a third boundary condition for our electron. And the third boundary condition results from the fact that the probability to find the electron anywhere in the one-dimensional box must be 100%. Okay. So now the question where the electron is becomes non-trivial when we consider the electron as a wave. Okay, because a wave is naturally spread out over space, and interpretation of the wave function that describes the electron is that and that's called the Born interpretation of the wave function, is that the square of the wave function represents the probability to find the electron at a particular point within the one-dimensional box when we consider again the particle properties of that electron. Okay. So now, because of that, the integral over the square of the wave function over the entire box must be 1. Okay. That would be equivalent to the statement of saying, well, we always have to be able to find the electron somewhere in the box. Okay, so the probability that the electron is somewhere in the box must be 100%. So mathematically, this boundary condition is phrased like this. So we have the integral between 0 and a for psi square dx, and that has to be 1. So now we can plug this, or combine this expression and our expression for the wave function. So basically plug our expression for the wave function into this equation here, and then a squared times sine squared n times pi x over a dx must be 1. Okay, and then one still needs to solve this integral, and I don't go here through all the mathematical steps because this is more subject of physical chemistry that covers quantum mechanics, or such other classes. But the result of the mathematical steps is that a is equal to the square root of 2 over a. So that means that the full wave function that describes our electron in the one-dimensional box is psi is equal to the square root of 2 over a times sine s n times pi times x over a. Okay, so this factor here, the square root of 2 over a, is also called the normalization constant for the wave function. Okay, because it normalizes the wave function so that the probability to find the electron somewhere in the box is always 100%. Okay, so now we have described our electron in the one-dimensional box. So now we have to make the step from the one-dimensional box to an electron in an atom. In particular, we look again at the most simple atom, the hydrogen atom. Okay, so now we have to think about, well, what are the similarities and the differences between these two problems. So now let's talk first about the similarities. So in the one-dimensional box, our electron was confined. It could not leave the box. Okay, for that reason, it behaved like a standing wave, similar to a standing wave. So in a hydrogen atom, we have a similar problem. Our electron is confined within the hydrogen atom, okay, because it's bound to the hydrogen atom. Under normal circumstances, it cannot leave the hydrogen atom. Okay, for that reason, it should also behave like a standing wave. We should be able to describe our electron again like a standing wave. But now, what are the differences between the two problems? So the first difference is that in a one-dimensional box, we have a one-dimensional problem, and in a hydrogen atom, we have a three-dimensional problem. That because a hydrogen atom is considered to be a spherical entity where three coordinates play a role: the x coordinate, the y coordinate, and the z coordinate. Okay, so that's the first difference. And the second difference is that in the one-dimensional box problem, our electron did not have a potential energy. So in the hydrogen atom, our electron actually does have a potential energy. Okay? Can anyone guess why our electron actually does have a potential energy and where the potential energy comes from? Pardon me?
The Coulomb potential.
Coulomb energy, yes, correct. So it's due to the Coulomb attraction between the proton and the electron. Okay. So therefore, we need to adjust our Schrödinger equation for the three-dimensionality of the problem and for the existence of a potential energy. Okay, and you see the Schrödinger equation for the hydrogen atom here. So you see that in addition to the term d square over dx square, we now also have the two other coordinates, y and z. So we have, in addition, d square over dy square and d square over dz square. So this factor here is just the same. We have seen this before, minus h square over 8 pi square m. So this is now our operator for the kinetic energy, which is now just three-dimensional. But in addition to that, we have now our operator for the potential energy. Okay. And the operator for the potential energy is E squared over 4 pi epsilon 0 times the square root of, well, x squared plus y squared plus z squared. So the operator of the kinetic energy plus the operator of the potential energy applied to the wave function, which is now a three-dimensional wave function, not a one-dimensional one, will again give the energy of these wave functions, which are now three-dimensional. So now this differential equation is much more difficult to solve in comparison to our previous differential equation. And again, I'm not going through all the steps here, but what I'd like to mention is that it's mathematically easier to solve the Schrödinger equation when you transform the Schrödinger equation from Cartesian to so-called spherical polar coordinates. And here's a brief illustration how the spherical polar coordinate system works. So we have here just a point in space. Okay, of course, a point in space can be described by the coordinates x, y, and z in the Cartesian coordinate system, but it can also be described by a distance from an origin and two angles, theta and phi. Okay. So now r, the distance, is nothing else but the distance of the position of the particle and the origin. Okay, so this here just would be r. Okay, so now theta here, this is this angle here. Okay, so this is basically the angle between the z coordinate and the line that connects the origin point. Okay, and phi is nothing else but the angle between the x coordinate and this line here, which is nothing else but a projection of this line here on the xy plane. Okay? So we can mathematically transform our Schrödinger equation Cartesian to polar coordinates, and it becomes mathematically easier to solve. Now the result is the following. The result you now also get in polar coordinates, and the result is nothing else but your three-dimensional wave functions that describe your electron within your hydrogen atom. Okay? Your wave function is then a function of r, theta, and phi. Okay? And we can separate this wave function into three parts. A radial part of the wave function, which is only a function of r, a colatitude part of the wave function, which is only a function of theta, and a azimuthal part of the wave function, which is only a function of phi. Okay. Now you see here the three explicit mathematical forms of the three parts of the wave function. We do not need to discuss these mathematical forms in detail again. That would go way too far for an inorganic chemistry course, but we should know that they exist, and we should know that they are now a function of three quantum numbers. Okay, so that's now an important difference to the problem of the electron on a line. Here we could describe our wave function as a function of a single quantum number. For an electron in a hydrogen atom, we need three quantum numbers. Okay, you all know these three quantum numbers. There's the principal quantum number n. There's the orbital quantum number L, whereby L can only vary between 0 and n-1. And there's the magnetic quantum number M, also often called ML, whereby M can vary between -L and plus L. So you see these three quantum numbers appearing here in these three expressions. You see that the radial part of the wave function is a function of the quantum number n and L. You see that the colatitude part of the wave function is a function of the quantum numbers m and L. Okay. You see that the azimuthal part of the wave function is only a function of m. Okay. So the product of these three describe the overall three-dimensional wave function that describes the allowed states of the electron in the hydrogen atom. So these wave functions in chemistry have a particular name. Can you imagine what I talk about? Orbitals, correct. So these wave functions are usually called orbitals. So just derived our orbitals that describe our electron in an atom. Okay. So now an orbital is only described by these three quantum numbers. However, we should not forget there's a fourth one that is required for the complete description of the electron in an atom, and that's the spin quantum number S or ms. So this is not a result of the Schrödinger equation because we don't need the quantum number S or ms for the description of an orbital. Okay, so within an orbital, the electron can either be spin up or spin down. That reflects to this quantum number ms, either be +½ or -½ Okay, so we can understand this quantum number best when we consider our electron as a particle here again. Okay, as a particle that can spin around its own axis and can either spin clockwise or counterclockwise. When it spins clockwise, okay, then our ms value is plus a half. When it spins, so when it spins anti-clockwise, ms is plus a half, and if it spins clockwise, then ms is minus a half. Okay, because our electron is an electrically charged particle, its spin around its own axis causes a magnetic field. So it behaves like a little rod magnet, yeah, that is either, well, pointed spin up with south pole pointing up, or spin down with the south pole pointing down. Okay, again, this is not a result of the Schrödinger equation. The spin quantum number was actually found experimentally. Was not theoretically derived. All right, so then I think we can stop at this point, and I just stop the recording. I would still be happy to answer any questions.